So I think we can start it now. Hello, everyone. My name is Li Zhang, and welcome to the session 5.5, Cost-Effective Multi-Sensor Positioning and Data Acquisition Technique. Some short introduction about myself. I'm a research associate at the Institute of Engineering Geodesy at the University of Stuttgart in Germany. I studied and got my PhD at the same university at 2016. My research interests are low-cost GNSS, quality modeling, digital map, and multi-sensor system for the transport telematic. I am the co-chair of the Commission 5 Working Group 5.6, Cost-Effective Positioning. And today I will chair the session with my colleague Günther Retscher, who will also give his presentation later on. And my colleague David, Kevin, as well as the FIG technical support, Marine, will support us during the whole session at the backstage. So that means they will, for example, keep an eye on the questions arise in the question and answer in the stage. So here, just to show you the schedule. Here we will start with the technical session. We have 19 minutes technical session, and after that is the so-called Ask Me Anything session or breakout session, where you can actually ask any questions what you want for half an hour. So I will just now start the technical session with some 4 questions. And after that is I will give you so there's 3 awesome live presentations, and you can pop your question and answer in question just in the question and answers in the stage. So there's 2. One is stage, one is the event. Please put your question just in the stage in the question and answer, not in the event, and they will be then answered after. And if all the 3 presentations ended. And then we will have one panel discussion with 4 panelists for about 14 minutes. So I think we can start it now. First, I want to start with some word cloud that you can see in your Hopin in the stage. I think there's one tab called word clouds, and here the question is, what makes a smart surveying? What is the smart surveying? What do you think? Because the topic of our working week is that smart surveying for land and water management. So what do you think? What makes a smart surveying, or what is the smart surveying? For example, you can write something like cost-effective measurement, positioning, high-quality measurements, and high-effective sensor fusion, ubiquitous positioning, Internet of Things, online services, software solutions. You can just write any other keywords. What you think is what makes the smart surveying? So I hope all of you can hear me. I just check the event. Okay, I think it works. Okay. Then I just continue. this. So then the next is we have 3 poll questions, and you can find them also in the stage. The first question, I don't know if it's already. It's ready, the poll questions. The first question is, which technology do you think will be the most important for the positioning and measurement in the future for the surveying? Unfortunately, it's only single choice, so that's why I asked you what is the most important technique for the positioning and measurement in the future. So, for example, low cost but high performance mass marketed oriented sensors, or what we have heard about yesterday is the augmentation services, GNSS services, or for example, software solutions, so GNSS software-defined receivers, or generally open source software, or the mobile mapping system, or the indoor positioning technique, and the terrestrial or the UAV-based laser scanning and photogrammetry, or none of them. You can just write this in the comment. This is the first poll question, and the next is the next poll question is how accurate the GNSS position could be by using the smartphone. So it's several meters accurate, or decimeter level, or centimeter level, or you don't know. The third poll question is, do you use more open source software or commercial software in your daily life work? The first option, more open source software. Second, more commercial software, or about 50%. So I think you have enough time to do your polls, and I will come back to the results, I think, just at the beginning of the panel discussion. Maybe I can check if the poll is already there, the poll question. Okay, great. Claudia has prepared them well. So think I can continue. So now we come to the 3 live presentations. As I mentioned before, we will have 3 presentations, and each is about 10 minutes. And again, I would like to encourage you to pop your questions in the Q&A in the stage, and I will say we will answer them, all of them, at the end of all 3 presentations, so that it's run maybe smoothly. And that means you have actually enough time to write your questions in the Q&A and hop in the stage. I think now I will stop to share my slides and introduce the first speaker, Günther. And Günther, I think you can prepare your screen or your presentation to show your presentation as when I introduce you. Günther is an associate professor at the Department of Geodesy and Geoinformation at the Technical University of Vienna in Austria. He received his, I think, his habilitation in the field of applied geodesy from same university in 2009, and his PhD in 1995. His main research and teaching interests are in the field of engineering geodesy, satellite positioning and navigation, indoor and pedestrian positioning, as well as the application of the multi-sensor system in geodesy and navigation. He's also the co-chair of the FIG Working Group 5.5 on multi-sensor system, and I know he's also very active in IAG. So today he will make a presentation about the study for the development of guidance and information system based on the Wi-Fi for his university. So Günther, the screen is yours.
Thank you, Lee. Good afternoon, morning or evening from my side. I will talk about a follow-up project dealing with Wi-Fi for the development of a guidance and information system of my university. So just as motivation, the TU Wien has over 12,000 rooms in 30 buildings. You can see most of the buildings here are around the inner city area, and especially the library is a big building with 6 levels and 1,160 square meters. And the aim of this positioning or navigation system and information system is that we want to guide users even to the bookshelf to find a certain book with a low-cost system. So it's a campus-wide navigation and information service integrated in the current information service and e-learning platform. So the selection criteria was that no additional hardware should be used at this stage. So we came up with the idea to use signals of opportunity, and especially as we have full Wi-Fi coverage, we can use Wi-Fi. It should be also be usable for common mobile devices such as smartphones and tablets, and a high reliability and coverage on the campus. And apart from user-friendliness, also data protection should be guaranteed. So we use Wi-Fi, and in the first stage we use fingerprinting. As you might be familiar, we have 2 different phases: an offline training phase, where we gather the signal strengths in the building, in the surrounding environment, and store them in a database and visualize them in radio maps. And in the online positioning phase, we do our current measurements, and using a matching algorithm, we can define the user's position. Here, the system training should be done only in dynamic mode. That means kinematic measurements. So when we look at signal observation of Wi-Fi signals, you can see here the observation of 6 different Wi-Fi access points or hotspots. And as you can see here, during the day from 10 a.m. in the morning, it's more noisy. There are higher fluctuations than during the night. So this is a 24 hours observation period. So we have a significant difference between day and night. And if you look at different smartphones, here we use 6 and 2 Samsung S3. We had 2 at the same model, so same device. So you can see even these 2 from the same type have some significant offset. So that's why it's very important to do a system calibration. We have to calibrate the smartphones. And here we use the multivariate linear regression for offset determination, where we have X as the current measurement of the signal strength, received signal strength indicator RSSI, and Y RSSI is the average value. And we have 2 coefficients. AS is the gradient, indicating the gradient. And when you look at the 2 different Wi-Fi signals, the 2.4 and the 5 gigahertz, you can see that there are some significant differences between the smartphone due to their heterogeneity and also between the 2 different frequency bands. So calibration is essential when we do Wi-Fi fingerprinting. When we look at the RSSI distribution of one access point, we can see on the left before and on the right after the calibration, we can see here that the variation range is reduced from 27 down to 16 dBm and the standard deviation from 5.2 to around 3 dBm when we do this calibration. Then we have to get these databases and visualized in the radio maps. On the right here in the top, you see two different radio maps from two different access points. And we can stack all these radio maps in so-called data cubes. As you can see here, for the example of 4 access points, we have 4 layers in this data cube. And from these, we can perform a matching to get the current position of the user in the online phase. We use the probabilistic matching approach based on the Mahalanobis distance. This usually provides an error accuracy than deterministic approaches, which are based on nearest neighbors, K, or weighted nearest neighbors. We use this Mahalanobis distance. You can see it here in the formula, and it has the attributes that we calculate the weighted square sum of the RSSI differences between the off and online phase. And then the weighting is inversely proportional to the variance of the offline fingerprint. Here are some examples. You can see here 2 test points. We have the estimated position denoted as a star, and the true location is a circle. And on the left, the estimated position is the true location. So you don't see a difference here. And the Mahalanobis distance is very small. It has only a value of 0.5 dBm in this case. On the right, you see a solution where the estimated position is quite far away from the true location. It's nearly 23 meters, and the Mahalanobis distance on the true location is about 10 dBm, and on the estimated position only 3 dBm, around 3 dBm. So that means even if the Mahalanobis distance is small, there can be a large variation. So we have to take this into account. Here you have an example positioning using the Mahalanobis distance. We have to look at the minimum distance, and for the 4 points, 1, 2, 3, and 5, we got the correct minimum. But for CP04, we have a minimum Mahalanobis distance at 0.3. So this would be a mismatched position then. Now some kinematic trajectories. On the left, you see a larger deviation here in the center. On the right, you see a better result. The problem on the ground floor was that we only have 2 access points here in this area. And the geometry is therefore not very good. And we would need additional access points to have a better geometry. Even on the second floor, where we have 4 access points, it would be better also to have additional access points of new hardware to get a better solution. But on the left, you can see a very nicely reconstructed trajectory of the user who walked around these bookshelves here. To have a closer look, a more detailed look on the positioning accuracy, we have calculated the grammar rail lower bound on the root mean square error. You can see it on the left for the ground floor and on the right for the second floor. So the low values in dark blue indicate higher positioning accuracy during the online phase, while the higher values in red mean lower accuracy. And as you can see, when you look on the ground floor, you have 2 different areas, like yellow-green, where this parameter is about 2 to 3 meters, and on the other areas, we have values of about 0.5 meter, maximum 1 meter for the positioning error. So this brings me to my concluding remarks. We can see sufficient stable access points all over the campus, but the RSS fluctuations can be plus minus 5 dBm during the day, and therefore the deviations from the ground truth are on the meter range. We have seen that the smartphone calibration is essential, and in the future now we are starting with it. We want to densify and rearrange the access point network, not only to get the full coverage, but we want to implement also new hardware for the Wi-Fi access points which are capable to perform range measurements. So this is the Wi-Fi RTT FTM protocol round-trip time measurements, and this should be implemented soon. And of course, we carry continuous RSSI recordings in addition, and of course, combination with other technologies like the smartphone sensors, what we have. And in addition, like when you look on book finding, we can use also radio frequency identification as labels for the books. So thank you very much for your attention.
And as I said, you can put your questions in the question and answer in the stage. Now I introduce our next speaker, Hossam Shitari. Hossam, you can just prepare the to share your slides while I'm introducing you. Hossam is a research associate at the Department of Geomatics and Geoinformatics at the Hafen City University in Hamburg, in Germany. He received his master in the same field of the university from the University of Stuttgart in 2019. So he was a very, very good student, our GeoEngine students, and he is working at now at the level 5 indoor navigation, while his main research interests are in the field of engineering geodesy, indoor and pedestrian localization. He's also involved in the field of artificial intelligence, geoinformatics, robotics, and 5G positioning. And today he will make a presentation about the smart surveying instrument using ubiquitous computing concept. It's very, very innovative, I think. So, Hossam, the screen is yours.
Thank you, Dr. Lee, for your warm introduction. And hey, everyone. This is Hossam Shitari from Hafen City University, Hamburg. Today, I'm going to present you the article titled UBT, Smart Surveying Instrument Using Ubiquitous Computing Concept. Today's a day, there are a variety of smartphones, includes many sensors, or capable to connect with hundreds of add-ons. You may see some of them in this slide. Let me just explain a few of them, maybe from right to left. Some of the CAD phones today's has a temperature, air quality sensor, or also built-in laser or camera to calculate distances. There are smartphones with up to 100x zoom capability. 2 camera systems, like in Leica, or measurement add-ons in Hoso Design, for example, is already a product. All of the mentioned devices are even more interesting when 3GP releases 16 and 17 of 5G technology with positioning capability will be available to public soon, which work both in indoor and outdoor environment. We assume that the smartphone usage in geometric application will be more handy in the next years. I think Professor Harald Stemberg will talk about 5G positioning later in more details, but let's now start this journey from some basics. For instance, total station or tachymeters. And back also to our experiments and what we have done. We tried to evaluate a predefined concept named UBT, stand for ubiquitous total stations, and we wanted to see how accurate one can measure angle and distances with smartphone sensors or add-ons. We compared the measurement with the total station, actually with the Leica TS16. Yeah, here we can see the methodology behind the angle measurements. The input was gyroscope, magnetometer, acceleration sensor values. The process was using a simple Kalman filter. We have used the gyroscope value in model equation and the acceleration and magnetometer ones as observation. The output would be then horizontal and vertical angle depends on the predefined axis. For distance measurement, it was more straightforward. We have used a disto and connected with a smartphone. Once user can press the measurement button, the disto start to work and send the measured value back to the application via a SMS protocol. It was a Makita disto with accuracy of 1 millimeter in range of up to 50 meters. Yeah, before we start the measurements, we could do some preparation. The standard deviation of phone sensors while the device remains standstill on a table can be seen here in this table in different axes which were important for our measurements. 3 different smartphone placement has been also designed. First, using a tripod and adaptive holder, just like an independent device or tachymeter. Second, attaching the smartphone to the total station to be sure about the exact value of the rotation as a reference one. Third, measuring with smartphone just in hand to understand the public usages of a smartphone performance. As a result, we have seen the mean error of 0.700 and 5.401 in degree in vertical and horizontal angle. It means 3 and 15% of deviation for the vertical and horizontal angle has been resulted. Altogether means 20 centimeter of mean positioning error in only 2 meters of object distances can be estimated. Yeah, as conclusion, we could conclude that UBT can be used to make total station more user-friendly, more smart, and up-to-date. UBT can make the surveying application even more public. It can reduce the cost for operator trainings. And at the moment, a smartphone-based solution can be used instead of a total station, but really depends on the application. Yeah, that's all. On behalf of all my colleagues in this project, I would like to thank you for your attention.
I think there's already also some questions in the chat, and we can come to this later on. Now
Sure.
I'll introduce the next speaker, Gary. And you can now prepare to show your slides, and I will introduce you now. Gary Lau Shu Hun has been practicing as an assistant professional land surveying in the Surveying and Mapping Office, Land Department of Hong Kong Special Administration Region. Mr. Liu has been practicing photogrammetry, surveying, and remote sensing. Now he is the assistant land surveying of the photogrammetry and aerial surveillance section. So Gary, the screen is yours.
Hi everyone, thank you for joining my presentation today. My name is Lau Jiwon. Together with my colleague, have been studying the application of backpack mobile mapping system for tree survey. First of all, why I'm doing the tree survey? In recent years, some papers stated that the detailed tree information, including location, diameter, and base height, Quan spec and tree height can support the economical, environmental, and sustainable decision for the site-specific management. And then the conventional field measurement are laborious and expensive for tree inventories. Also, the Hong Kong government has begun to explore the use of advanced technology for the tree inventories. So that in this paper, we evaluate the accuracy and the feasibility of the backpack MMS for the tree inventories in a challenging environment. Now, we are going to introduce the pilot test area. It is a tree site along the Tsui Tsuk Street, Wong Tai Sin in Hong Kong. The testing site is a roadside artificial slope with an area of about 0.6 hectares and the gradient is of about 32 degrees. It consists of 7 berms and 1 staircase along the berm. The stairway from 3rd to 7 berms was very narrow. It was about 0.5 meters. There's about 250 individual trees, and the tree heights range from 3 meters to 15 meters. And that's about 85% subject area was covered by the tree canopies. Due to 85% subject area was covered by the tree canopies, we selected the SLAM-based backpack MS in this project. In order to minimize the accumulated error, the survey was split into several parts. The survey point cloud data in different parts were aligned using the cow-to-cow registration, so we should have a sufficient overlapping for linking out the scan. As SLAM-based backpack MMS is in the local reference frame, we use the point cloud along the Tsui Tsuk Street captured by another GNS and INS-based backpack MMS to georeferencing the scan data to the Hong Kong 1980 grid system. Here is the point cloud data of the georeferencing backpack MMS data. Now we can see that this is the staircase from the ground level to the 3rd level. Now we can see the point cloud of individual tree. In order to evaluate the accuracy of the backpack MMS data, reference point cloud were surveyed by using terrestrial laser scanning (TLS), with the control point established by the conventional traversing and leveling. The evaluated results will be discussed further. Lastly, we extracted the individual tree scan to collect the tree information data. In order to evaluate the accuracy of the tree attribute data, we select 38 individual tree attributes, such as location, dBH, and the Quan spec from the SLAM-based MMS data, and the TLS reference data for comparison. The root mean square of the tree height is 0.155 meters, and the quartz spread is 0.235 meters. The results show that the tree attribute data extracted from the backpack MMS data are high qualities. The reason of the large discrepancy in the quartz spread and the tree height measurement, it could be the laser beam of the LiDAR equipment may not be able to penetrate the canopy, so that the data was incomplete. In this pilot, the stem-based backpack MMS was used for the urban tree inventories in Hong Kong. The survey was completed in 2 days, which covered the slope area about 0.6 hectares with 250 individual trees. The errated results showed that the tree attribute data extracted from the backpack MMS data are high qualities. However, the vertical positioning error will increase dynamically in the slope top area. It could be limitation of the single head LiDAR equipment in the challenging environment, accuracy error in the span-based geofencing, or alignment error in the cow-to-cow registration. It's believed that the backpack MMS data will, with new LiDAR heads, and the better survey planning will improve this situation. This is all my presentation.
Now we come to the question and answer session for all 3 presentations. Think maybe we can invite all the 3 presenter speakers on the front stage. Okay, I start with so there's the questions from in the chat from David. What for is the question to the presentation? So what is the range for Wi-Fi indoor positioning and recommended base distance between the course and base stations? I think this question is addressed to Günther.
Yes, the range of course depends very much on the surrounding environment, but usually you can get up in inbuilt environments like 20 to 30 meters, and in outdoor you can get up to 100 meters or even longer.
Mm-hmm.
Depends how many walls you have in between, of course.
Mm-hmm. I hope this answers your question. I think there's another question for Günther. Is other an apps developer wants to develop another navigation app in the campus? Will they need to develop the whole thing all over again? Can the Wi-Fi infrastructure be shared easily?
Yeah, this is integrated in the information system, what we call TIS, and the e-learning platform Tuwel. It's based on Moodle, and of course we use Wi-Fi for the positioning and future technologies, as I said.
Mm-hmm. Okay, then I have one question here for the 3rd presentation. How do you segment or extract the 3-point cloud from the data? What is the challenge?
To extract the LiDAR data is very difficult in the tree site area. So we will separate in the different part of the berm, After we separate in the different parts, we can use the cross section to see every individual trees, the diameter and the DBH and the crown spread. In recent year, some technology such as the tree segmentation is developing, but this technology is not very good enough. So we are going to studying the later for the extract the tree information.
Okay. We have now a lot of questions. It's good. And now the next question addressed for the Hosum. Should the UBT be low-cost total station?
Yeah, it can be a low-cost total station in soon future, and also address to the question about the photogrammetry-based solution. Yeah, also to start and have the initial pose of the smartphone, one can use the photos and computer vision or photogrammetry application to initialize the direction and even the position of the smartphone. I would assume that we will see more about smartphone and surveying in the soon future.
Yes, I agree. And the next question is for the third presentation, Gary, where presented work have the relative size such as tree trunk diameter being evaluated?
The first question is this the backpack MMS? Is this LiDAR scanner? Yes, this is the LiDAR scanner. But this is a single head LiDAR scanner. The second question is
it's about relative size, the tree trunk diameter.
I think the tree trunk diameters it depends on how much laser scanner cover the tree. If over the 15% cover, we can make sure that the diameter can be measured. But if the laser scan point is not covered about 15 or half, I think the diameter cannot sure is accurate.
But I think this is also the information that you are interested, or?
Yes.
Okay. Yes. Okay. The next question again to Günther. How did you deal with the interferences?
Yeah, we deal mainly with it we do continuous RSSI observations in the environment. So we used, for example, Raspberry Pi units who continuously record all the Wi-Fi signals of all the visible access points.
Okay, the next questions, Günther again, have you compared Wi-Fi indoor positioning with any other approach such as UWB, especially on the aspect of accuracy and reliability?
Yeah. In our campus, we didn't use ultra-wideband yet because it's not a signal of opportunity, I would say, because we don't have the hardware yet. But in some other studies, we used ultra-wideband, and of course, this is much more accurate than Wi-Fi. But the integration also with Bluetooth is a topic now because we will install in some areas Bluetooth beacons. So we will work on the integration with Bluetooth ranging measurements, Wi-Fi RTT, round-trip time measurements, and signal strengths in the future.
I think it's just amazing how many sensors so we can we have within our smartphone, and how many things we can do as a surveyor.
Yes.
Okay, maybe is there any other questions? I think I haven't missed any questions in the chat. Maybe I have small question to Gary. I think you have said that. So the first question is there any requirement how accurate the tree height and also the crown spread should be measured?
It's for the tree height, it's very difficult to say that, because the backpack was operated in under the tree, so that some not many point cloud can penetrate to the tree head. So we can not sure that the tree height is very correctly. For example, if use the other instruments such as UAV LiDAR, it can be solve this question, but also they only have the tree, the point cloud data on the tree at the top of the tree, but under the tree is the data is not correct, cannot collect. So I think if really want to measure the tree height, can be combine the UAV and the MMS data.
Yes. This is also the idea. I think you can, maybe if you have UAV, you have some point cloud from the above, from sky, then maybe you can combine them together.
Yes.
Okay, great. Thank you.
I see there's another question for me.
Mm-hmm.
The question was, do we have to calibrate each device? So when we have the same model of smartphone, I have to say yes, we need to calibrate, as we saw also these two Samsung devices, which were the same model. They can have some offset in between. Depending on the accuracy, you can have a calibration for one model, but then it's not so accurate as if you calibrate each single device.
Mm-hmm. Thank you. I think we have a lot of questions. I think I need to take care about of the time, and I will say maybe we can try to answer them at in the Ask Me Anything session after that. So I just keep these questions for that, and now I just want to move to the panel discussion or the presentation. So I think I can show my presentation again. So first I want to introduce them for panelists. So I think I've introduced myself already, and now I want to introduce Leonid. Leonid Lipatnikov is the research at the Siberian State University of Geosystems and Technologies, Novosibirsk in Russia. He defends the PhD in 2014. He has been the chair and co-chair of the FIG Commission 5 Working Group 5.6 Cost-Effective Positioning Science 2015. So Leonid and I am chairing the working group together. His sphere of the research interest is the precise positioning with the GNSS. Then I'm happy to have Alison here. Alison is a professor in School of Science at RMIT University in Melbourne in Australia. Alison is currently president of the IAG Commission for Positioning and Application, and the co-chair of the FIG Commission 5 Working Group 5.5 on multi-sensor system. So she and Günther, they are chairing this working group together. Alison is technical representative to the Institute of Navigation in the US and is on the editorial board of the Journal of Navigation in UK, and also in the Journal of Applied Geodesy and the Journal of the GPS Solution. So very famous journals, all of them. Alison is currently interests include wireless sensor network, sensor fusion and estimation theory, high precise GNSS, collaborative positioning for the intelligent transportation system, and GNSS quality assessment. So here you can see she has very, very broad research views and very active at the different international organizations and journals. Then I want to introduce Harald Sternberg. Harald Sternberg studied and obtained his doctorate at University of Federal Armed Forces in Munich. The topic is on determination of trajectory of land vehicles with hybrid measurement system. This was followed by an academic appointment at Hamburg University of Applied Science, where Mr. Sternberg had the professorship for engineering geodesy and later headed the Department of Geomatics STEAM. In 2006, the department became part of the newly funded Hafen City University Hamburg. And from 2009 to 2017, Mr. Sternberg was the university professor of engineering geodesy and geodetic methodology. In 2017, he took over the professorship of hydrography and geodesy. Mobile mapping system, various carriers such as cars, ships, and indoor tourists, and the use of the local sensors for positioning, navigation, and environmental data collection are part of his research area. Indoor positioning, also using the 5G and monitoring of structure and focus of his engineering geodesy activity. He's also deal with the analysis of mass data with the help of artificial intelligence. Our speaker, Haysam, is also working in his team. In the field of hydrography, he works on the autonomous underwater vehicles, the automated analysis of the underwater images, and interpretation of the backscore data. And Mr. Sternberg has also been vice president for teaching and digitalization at the Hamburg University, Hafen City University, since 2009. So maybe I need to ask you, if I have time, how you find the work and work balance, and you are really doing so many fantastic researches, and at the same time also taking over so important administration task. So I think here you can see we have three topics here on the slides. The first one is about a cost-effective measurement technique, and I will start a little bit with the low cost cost-effective GNSS, and Leonid will follow up with a more ongoing project using the cost-effective measurement technique. And he will also introduce a little bit with the future work of the working group 5.6. And Alison will cover the current trends of the multi-sensor system, and maybe also a little bit about the future work of the working group 5.5. And at the end, Harald will introduce his research on the indoor positioning with 5G, because I know you have got a big project in this on this topic. I'm really looking forward to your presentation. So before I start, I think we can come back, have a look to the poll questions that we have. Maybe you can look at what we have got up from the point cloud. I think you can also see this from the stage. Just on the point cloud, a lot of so easy transferable data, intelligent technology, ubiquitous. I think I can see how many response they are. Oh. So there's a lot of keywords, indoor positioning, precise, redundancy, technology. Yes, very interesting. And maybe to the poll questions, number one, which technology will be the most important for the positioning and measurement in the future for surveying? 8 for the low cost but precise mass magnet oriented sensor. Maybe can. Oh, it's even more. No, 11. It's actually 11. About 1/3 is choose the low cost but precise mass magnet oriented sensors, and 3 for the augmentation services, and also 7 for the 20% for the indoor positioning, and also 20% for the UAV based laser scanning and photogrammetry. So very interesting. And about the results of the poll question 2, how accurate the GNSS position by using the smartphone could be, is 11. So 30% for the several meters, 44% for the decimeter level, and about 25% for the centimeter level. I think I will just come back to these results, and I hope I can answer this question in my presentation. And also, I think for the discussion later on, this may be interesting. So, do you use more open source software or commercial software in your daily life? So, 25% write open source, only 16% write commercial software, and about 50-50 is about 60%. So it's also very interesting. Maybe we can also discuss it in a panel. Okay, so I think I will just start my presentation now. So About the results, so I can remember about the results of our poll question. I can remember the results of the poll question of one technical Commission 5 session yesterday, the augmentation GNSS session. The question is to ask which accuracy that you need mostly for your application. Most of the audience answer that they need centimeter to decimeter accuracy. I think you know that to get the centimeter to the decimeter level accuracy from the GNSS, that the key is that you need the carry phase measurement. They should be accessible. And I will say at the beginning, maybe about 20 years ago, the carry phase measurement is only accessible on the geodetic receivers. And as I start with my PhD, there are already several so-called low-cost GPS receivers available on which the carry phase measurements are accessible. One of the famous provider is here the u-blox, and they cost only a couple of €100, and they can get the millimeter to centimeter level accuracy for the short baseline measurement. That means you can actually use them for the deformation monitoring of some small objects. And you know that the trends of the hardware, they are even cheaper and cheaper, and you can get much better hardware for less money, and they have actually more functionalities. As I start my PhD thesis, the newest u-blox receiver is the LEAT60, which can only receive the GPS and only single frequency L1. And now the latest u-blox receiver is actually this F9P, which can receive multi-frequent and multi-system and multi-frequency. And you can you get this kinds of course, you can get also this kinds of the receiver from the low-cost receiver from the other manufacturers. The similar things I think is happened with the IMU sensors, also with the laser scanners, and the trend is of software is also there's more and more open source or free hardware they are available. I think this you have shown that a lot of people, a lot of you use both of them, commercial and open source. For example, for the GNSS, they are famous is the RTK-lib and the TEQC, etc. Actually, I'm just thinking at that time that the hardware is, of the GNSS is already quite cheap for the geodetic application, but maybe they are still not cheap enough for the mass market. In 2006, Google announced that the raw GNSS measurement will also be available to the apps in the Android operation system on the smartphone. It's something like the game changer because after that, since 2017, there are a couple of smartphones which can provide the multi-frequency GNSS carry phase raw data. But at the beginning, it's only single frequency, as you can see here. And in 2018, the Xiaomi 8 is the first smartphone with the dual frequency. At the same time, there's also a lot of free software, open source on the app, free apps available, which can help you to log the raw data on the smartphone. It's very interesting if you maybe some of you also know this graphic from the GNS from the GNS market report from the GISA, European Global Navigation Satellite System Agency. So here you can see the this figure, and it shows you that the growth of the total GNSS revenues from the 2019 to 2029. The growth is actually mainly due to the revenues from the mass market device. That means the GNSS device less than 105 115 euro, and also from the augmentation services. And I think maybe you have also joined the excellent technical session about the GNSS augmentation services yesterday, and it's very interesting from the. So there's really now a lot of development and also in this area. And if you look at this figure about the cumulative revenue by segment, we can see that the road and customer solution, they are dominating. In combination, they are more than 19% of the market. And I think you know that revenue in the road segment is actually mainly due to the ADAS, so the advanced driver assistance system and automated driving. And the customer solution revenue is mainly come from the smartphones using the location-based services. So I think the future is really the mass market. And here I just take the, I think I just take two examples for the application in the road segment, or actually here for the road transport security. So the application of the low-cost GNSS for the road transport security. I just take these two projects as example, just because I'm the institute which I'm working at is joined the project, so I know a little more about them. So one of the project is called the Transec, and the goal is to prevent the terror attack using the tracks which were happened in Nice and in Berlin. The other project is called Ghost Hunter, to detect the wrong-way driver. Both projects need actually a lane precise localization of the vehicle. It means some decimeter level accuracy of the vehicle position is necessary. And not only the positioning, but also the digital map is plays also a very important role. We know also that there are a lot of ongoing development in the high definition maps, HD maps, HD maps. So they want to get some decimeter level accurate digital map. And this is also in this area, I think we, the geodesists or surveyors are very active. So here you can see that for the positioning in the Transec, the u-blox receiver, we use the u-blox receiver and Xsense IMU, which are both cost-effective and low-cost. And for the multi-sensor integration, we use the ROS, the robot operating system, which is also the open source. And in the Transec, here the Xiaomi 8 smartphone was used, and here is actually for, let's say, for this application, we have said that actually the decimeter level accuracy is enough for the local precise positioning. But as far as I know, some of the weakness of the smartphone is actually their antenna. And I know that some researchers just use for example, an external high-end antenna, or just put this smartphone on some chokering with open sky, very short baseline, and you can really even get a centimeter level accuracy, which is really amazing. So I think I will end up my presentation and hand over to Leonid, who will introduce more exciting project dealing with the cost-effective positioning and measurement. So Leonid, the screen is yours.
Thank you. Do you see the slides? Can you see?
Leonid, I don't see anything. Did you push the button for sharing?
Yes, I tried to share.
But I do not see anything coming up here.
I choose the whole screen and push the button share, but it is like it's not active. Maybe it is in progress because I don't have my internet connection. Maybe is not fast enough.
I don't see anything coming here. So perhaps.
Okay, I see.
Oh, that's coming. Yeah.
Okay. Is it okay? So I will tell a little bit more about projects which are currently performed within the working group 5.6. Thank you, Lee, for introducing the cost-effective position in general and for telling us about some low-cost, precise sovereign solutions. So the first project I'm going to introduce is low-cost GNSS equipment for environmental and engineering monitoring. The motivation for the project is actually the situation around climate change, and this equipment was developed particularly for geodetic monitoring in remote areas with harsh environment in Siberia. You know that because of climate change, the permafrost is melting actively, and we have an urgent task of improving monitoring of engineering infrastructure in the north. So we needed a new solution for monitoring because what we have right now in the market for that purpose is prohibitively expensive. So actually, this project is done at our university by people who aligned themselves with working group 5.6, not by me particularly, but by other people. Nevertheless, we work as a team. So the key features of the equipment is a low-cost GNSS receiver. Right now, it includes U-blocks, original equipment manufactured board, and but actually it is compatible with other modules. Also, it includes open source software, which is has been already published on GitHub, and I will provide a link to anyone who's interested. It is intended for completely autonomous monitoring, and not all the stations within the monitoring network need to be connected to the internet because we have a radio link between them. And the key feature of it is that the equipment can work under really harsh conditions. We tested it for a year in Novosibirsk, and sometimes temperature dropped to minus 44 degrees Celsius, and everything worked fine. The precision was at about 8 millimeters standard deviation in height, and can be improved if we. That was the line of 10 kilometers. The precision can be improved if we changed the GNSS model. The second project is actually an addition to the first one. It is open source software and hardware inclinometer based on video recognition and tracking of a bubble in the bubble speed in the speed level. The bubble is tracked with OpenCV software, which will be open source. Right now we are in test phase, and also we refine the calibration procedure. Again, it is done by people within the working group 5.6. And another project, the third one, which is done by Sergey Dolin, and I'm his research supervisor. He's a master student right now, PhD student. Actually, we try to implement an idea proposed by Chris Rieses, Joel van Kronenbroek in 2019 at FIG Working Week. The paper was called "The Uberization of the GNSS Positioning Infrastructure." So what we try to do is basically to organize a collaborative network in which every participant can be a base, can play a role of a base station if its coordinates are well defined. What we achieved up to now is shortening convergence time in PPP to a couple of minutes, even without ambiguity fixing, resolving and fixing ambiguity in PPP with the same additional information is the next step. So the main principle of this is PPP plus RTK on demand. And we are going to publish results of those projects at the cost-effective positioning seminar, which is planned for November, December this year. And everyone is welcome. It will be online and offline in Novosibirsk if someone wants to travel. Everyone is welcome. The cost is zero, so it is very cost-effective. And a couple of words about our next activities. We are going to shift slightly the focus of our working group and concentrate not only on a broader topic of developing cost-effective solutions, but more rather on open source software and open design hardware. And my point is that the most important part of our future work is providing the framework for transparent and comprehensive evaluation and comparison of surveillance solutions. And how to provide it, I would like you to join the discussion at the AMA session, and I think we can discuss and define what we can do together to achieve these goals. Thank you.
Can you see this?
Okay.
Alison? Can you see the slide? Can you see a moment? Can you see the slide?
No, I can't see the slides.
No?
It's coming up now, Lee. Thanks very much.
Okay. Yeah.
Okay. Okay, so thanks, Lee. And following on from the last presentation, I guess what we're looking at in working group 5.5 is really where are the trends heading in sensor systems that can contribute to improving positioning performance. And when we look at positioning performance, we're looking at positioning performance beyond the concept of can we improve the accuracy. We want to improve the availability, we want to improve the continuity, and we want to improve the integrity. So we're casting a broad horizon scan across what technologies are available, what signals of opportunity are emerging, and what are the best ways for us to incorporate these. So if we start from what we know, which is the capabilities of GNSS, and we know that developments in multi-frequency, multi-signal GNSS, multi-constellation GNSS are driving performance levels in new directions. But we also know that GNSS signals suffer from similar vulnerabilities, intentional and unintentional interference, the error sources we understand. There are certain environments where no amount of signals from satellites, no amount of new constellations going up are going to overcome the limitations. Urban environments, underground tunnels, underwater. And so the shift has been to looking at the sensors that can be combined, where we do sophisticated error modeling. We look at the uncertainties and balance the strengths and weaknesses of different sensors. And we've heard presentations on Wi-Fi. We know about inertial navigation sensors, and the multi-sensor solution kind of led to a concept of ubiquitous positioning. And I seem to recall when we started this working group, it was actually called ubiquitous positioning, because the idea was we could take all the measurements from all the sensors, combine them in an optimal estimation approach, and generate a solution. As signals of opportunities have expanded, as we started looking at the signals that were out there that we could combine, Bluetooth, we'll get a presentation on 5G after this. We have the opportunity to look at signals and kind of go, well, what are the performance requirements that we're trying to meet? And what are the signals that we can combine in order to help us achieve that? So redefining the idea of what is ubiquitous to be what is fitness for purpose for the application that we're trying to design a solution for. And this is where we come up with the idea of the network approach. So moving away from single platforms to where we have multiple platforms with multi-sensor systems on each of the platforms, the so-called network approach or the so-called collaborative positioning approach. Can I get the next slide, Lee? Thanks. And to support this work, the kinds of activities we've engaged in this working group is to set up a series of field campaigns. Now, as you can imagine, multi-sensor, multi-platform, you know, this whole idea of any application where we want to deliver GNSS-like performance in GNSS difficult environments, this is a massive and diverse problem to solve. So our approach in this working group was to pull together resources from a bunch of universities, from a bunch of well-known researchers who were conducting their own research into these areas, to combine these efforts into these field campaigns that allowed us to examine more broadly the issue of multi-sensor, as well as multi-platform, and ultimately this kind of collaborative approach. We started this in 2012, where we had the first campaign in Nottingham, and we had one in 2017 in Ohio State University. We had a couple scheduled for last year and for this year, back in the US and in Australia and in Vienna. And we obviously, due to COVID, we've put those on hold and started focusing a little bit more on how we actually build the algorithms and the strategies for handling three things. One is the sensor modeling themselves, understanding the probability distributions of errors associated with the sensors, and then looking at the nonlinear filtering and estimation approaches that could help us to generate more robust solutions. Can I get the next slide, please? So with a strong focus on developing or connecting in all the capabilities in these field campaigns, you'll see that we've constructed some fairly complex experiments. You know, people carrying around backpacks with a full suite of sensors on there, or platforms that are more kinematic with complex dynamics models that are also fitted out with multi-sensor systems. But what we're actually interested is in the sharing of information between these platforms. So people carrying sensors on backpacks, platforms that are autonomously navigating, we want them to share information in kind of a really big geodetic network. And we treat the multi-sensor cooperative positioning algorithm in that way, as a very big geodetic network. And we want to build it so it's scalable in the same way we do partitioning of survey networks. We want them to have the same properties of survey networks in terms of how we do the adjustment and how we test the validity of the adjustment to ensure we have the optimal results. Can I get the next slide, Lee? And here we see another experiment. This was the test we ran in 2017 at Ohio State University. And this was where we started to kind of look at defining more clearly where the problem sets were. We know that if we're navigating in an outdoor environment where we have clear visibility of the sky, we know that we could have GNSS as our primary navigation system. We know when we go inside, we can use technologies like Wi-Fi. We know we're not going to get GNSS in an indoor environment, so we can use something like Wi-Fi. But what happens in the transition zone between indoor and outdoor? Can we detect the transition zone in such a way that it allows us to determine which measurement set we actually use? Can I get the next slide, Lee? And building these multi-sensor systems so that they're incredibly robust and portable and low cost, all the things that we're talking about in this session, present real challenges if performance is ultimately what we're looking after. So I'll just go to the next slide, Lee. Ultimately, being able to develop that benchmarking range, if we understand which sensors will give us what performance at what probability level, then we know what we can use it for. So this working group is actually established to define the characteristics of performance so that fitness for use then becomes a viable prospect. Thank you very much.
Thank you. Thanks a lot. I think now is the Harald's turn.
Okay, thanks a lot, Lee, for the introduction and the invitation to talk about positioning with 5G in the last 3 minutes. Why 5G? With the 5G, we have a further development of the 4G or the long-term evaluation part, and there are 3 main important applications for this 5G. We have the enhanced mobile broadband. This means that we have high data rates, so we can transfer a lot of data in a short time. We have the massive machine type communication. We can have many connections with low data rates at the same time, so we can use a lot of smartphones in the building. And we have the ultra reliable and low latency communication. This means that we have reliable connections with low latencies for the data transfer. And this 5G in indoor navigation, we can do this indoor navigation by using the 5G in combination with smartphone sensors and GNSS, so that we have this smooth transition from outdoor to indoor, as Alison mentioned before. And we have the positioning protocols from 5G, and so we can use with the smartphone sensors like the acceleration and the gyroscope to provide a precise or an accurate position for the person. And in combination with these enhanced mobile broadband, we can transfer relevant data like the maps for the navigation of the building. So we can transfer the data of the buildings we are entering just in the moment we are entering the building. The 5G based positioning is like in the 4G network system, but we have some advantages because we have more information. We have not only an angle of arrival, but we have a downlink angle of departure, and we have an uplink angle of arrival, for instance. So we have just more data, and in the new 5G protocol, there's also a positioning in the in the protocol. So we have these calculations from the network. In our project level 5 indoor navigation at the Hafen City University, we will have a 5G non-standalone campus network in the building. And for this, we have on one side the outdoor and an indoor network with a frequency of this campus network in the range of 3.7 to 3.8 gigahertz. And we have an additional LTE anchor band. And for the use, we have 4 outdoors antenna, and we will have several indoors antenna. Why we have to use both of them? If you're looking for this outdoor coverage with 3.7 gigahertz, you can see that you can't enter the building. It's quite difficult, but you have a quite good measurement outside the building. There you have GNSS, there you have 5G. You can use this 5G positioning to go indoor, and indoor you have a quite good 5G indoor network, like here with the simulated coverage on the 4th floor, where you have...
Sorry, Harald, I have to stop you because of the time. I'm sorry for that, but you can...
I'm sorry for that.
You can go to the AMA session and then perhaps present also there.
The last
Sorry,
part.
Harald.
Yes.
Yeah, I'm sorry, but time is, and we have to use this for the next session also.
I'm sorry, Harald.
Okay, no problem.
So we stop here and go to the session.
Other session. I think the link is in the chat.
Yes.
Okay, sorry. I keep the time.
Okay.
Entschuldigung.